Welcome everyone to our third geometry seminar. So today we are very lucky to have Dr. Ashim, who recently joined as a permanent faculty at Bragg University. So Dr. Day did his undergraduate in statistics from Dhaka University, and then he went abroad and did a master's somewhere in Texas, and then did his PhD in UTD, University of Texas in Dallas. And after his PhD, he was a tenure-track faculty at University of Texas in San Antonio.
El Paso.
Sorry?
El Paso.
El Paso. So, and he was also a visiting postdoc at Princeton University. So, Dr. Day is working on the cutting edge of statistical analysis, and we are very excited today to learn about topological aspect of data from him. So please let us welcome Dr. Day.
Thank you so much for the nice introduction. I'm a little bit nervous because people are like expectation is really maybe very high. So I think it's very like fundamental or preliminary things, and I would say it's very applied compared to.
We like fundamental and preliminary. Yes.
So yeah, let's get started. Thank you so much. So yes, sorry. I think I should move that. Yeah. So today I'm going to be talking about a new anomaly detection algorithm for a dynamic network of transportation system. So this is the outline. First, I will briefly talk about complex network. Then I will talk about different tools and techniques of topological data analysis, we call TDA. And then I'll talk about our proposed algorithm for anomaly detection. And so we actually apply this algorithm to a data set, mainly it's called Harris County, Texas, in the period of Hurricane Harvey. So we want to check how this algorithm works in that situation in the transportation system. And finally, I will conclude and will show some future direction of the current work. And I'm telling you that please stop me anytime. So if you have a question. So we can represent different complex system like transportation system with a network. Okay, so for example here, so with a graph G, right? So here B is the set of nodes in the network, and E is the set of edges, and omega is the edge weight. Okay, so it's like the volume, and N is the number of nodes, total number of nodes in the network. And we can represent the connection between different nodes in the network by n by n adjacency matrix. Okay, suppose two nodes are connected with an edge, then the corresponding elements will be the corresponding edge weights. Okay? And if two nodes are not connected, then corresponding elements will be zero of this. Okay, so this matrix. So we are working mainly on this matrix. Okay, and for simplicity, we assume that this network or graph is undirected. For example, here we have an example of US airline network on May 5th, 2020. So here nodes represents airport, and if two airports have direct flight, then they are connected by an edge. So as you see, they are like, it's not very dense because of COVID pandemic. So this is like, yeah, so many of these edges are deleted because of COVID. And so this is the summary. The thing is, how can we summarize a network? Right? So this is like commonly used summary statistic, we can say, of a network. So one is called degree. So let me quickly write a small network. Maybe it will be clear. So suppose I have a small network. So something like this. So I have this network. So the degree is actually how many connection a node has. For example, for this node A has two connections, right? So that means it has degree 2, something like that. And the degree distribution is like, so degree distribution pk is the fraction of nodes in the entire network who has degree k. Okay, so it's like a frequency distribution things. And then we have another measure called average path length. Like, so this is the thing, think about for this node, and this is node maybe B. So I want to go node A to B. So what is the shortest path I can take? So this is the shortest path here, right? So it's 2. So I can say this is Dij. Here DAB is 2, right? So suppose we have n nodes, so we have n times n minus 1 pair. So if we compute all this distance, and I am taking their average, so it's the average path length or average shortest path length, sometimes we will say. Okay, and then last thing is called diameter. So when we compute this Dij, I take the maximum. Okay. So maximum of minimum distance between two nodes. Yes.
Does omega play a role in the definition of
No, so it's like a connection. I am ignoring the edge weights here. Only the connection, 0 and 1. Okay, so this is the summary statistics, you can say. And another important thing of a network is called network motif. So it's a small subgraph in the network. So suppose here, so you see that this is we say M1, so this is the one subgraph, but the condition is it is induced subgraph. So the idea here is I'm looking for one small subgraph in the network. Think about this subgraph, right? It's a triangle. So if I take only these two edges like this, right? This is not a motif, because I should take this edge also. I should take as it is. So this is a motif. Okay, so induced subgraph, and and these are the all 6, right? 4 node connected motifs in the network. And sometimes we compute their motif concentration. It's like relative frequency. Okay, so in the network. And I would say this is very important properties in a network, because we can study the local interaction of different nodes with this motif.
Could you please explain the motif again?
Yes. So as I'm saying that, so it's like induced subgraph. This is fine, right? So now think about this diameter. So diameter, when you can compute diameter, right? So I am using all this information, right? So and suppose from here to here, it's like maximum of minimum, right? You see that? But for motif, we are only considering local interaction. So think about a big network like 1,000 nodes. So you are considering how these nodes connect locally, right? So if you are focusing on local interaction, so you can say like local geometry. It's maybe not like mathematically correct word, but so local geometry you can compute by motif. So I'll give an example in the later of this talk. So so this is the.
Sorry, can I go back?
Yeah, sure.
You said all 4 nodes connected.
Motif in a network.
So you're saying that there cannot be any more motifs than these?
4 nodes.
4 nodes?
Yes.
Yes.
So there can be some other pattern as well, right?
This is all connected.
I see.
So all connected. These are all 6. If you take all 4 nodes, then this is the all the sets. Yes. Yeah. So I'm saying that 4 nodes because it is not easy to compute higher order motif. Okay. So so if you check like let's check 10 node motif. It's not easy to compute.
How do they grow as
So that's I really don't know. The algorithm is not
is
like
it
that.
exponentially or something?
Yeah, I think so. Yeah, so it's not easy to compute. So people still, we are working on this 4 node, maximum 5 node, and so on. So this is the always the argument, lower order versus higher order structure of a network. So as you see, this node distribution or average shortest path length is give you a like global properties of a network, right? So as I told you that if we want to focus on locally, what about the interaction locally? Then you need this motif or something else. right? Which actually focus on local interactions. And another important thing that in a network, the existence of motif is not random. It's not like occurring by chance. So they have significant functions in the organization and different function in the network. So this is very important thing. So we may think, okay, they are maybe occurred by chance or random. This is not the case. Okay, so think about the power grid network. So a motif actually has significant function in the power grid. So yeah, we have one paper on that. It actually published in Proceedings of National Academy of Sciences. So we actually see, okay, the robustness of power grid network, how it based on network motif. Okay, so now let's talk about the temporal network. So still now I'm talking about one network, but now think about that we have a time series of network. Okay, so think about the transportation system or airline network, US airline network, right? So I want to check how they change over the time. Okay, so it's like a time series of network. So at each time t, I have a defined network. Okay, so like this. At time t1, I have this network, and it's slightly changed at time t equals to 2, and so on. Okay, so you want to study how, like, whether anything happened in the network or not. So this is the main goal in this talk, that I want to check whether there exists any anomaly in any snapshot of this network. Right? So this is temporal network. Sometimes people say dynamic network. So yeah, this is one example of this dynamic network. This is like 2 time points, February 2, 2020, normal period. Like, so this is the US airline network, looks like. Right, so it has, as you see, that 340 nodes and more than 18,000 edges. But in the pandemic, if you check at May 3, it reduces 4,000 or around 5,000. Right? So again, if I want to check after 3 months again, right, and 3 months again.
So the parameter t has to be discrete. It's not computational.
That's right. So because it's computational, you cannot. Right. So still, for this very dense network to deal with this, like you have to have like a good computing power. So this is the example. Okay, let's then briefly talk about topological data analysis. So TDA, we said, is a new emerging field which actually works in the interface of algebraic topology, statistics, machine learning. So the idea here is, so it actually improves our understanding about hidden rule of, I should say, geometry. Sorry, I don't know its exact word or not. So geometry and topology. So in the organization and functionality of a complex system. So this is the 2 things, organization and functionality, right, of a complex system like transportation network. Okay. So there are a couple of advantages here. So it studies in a coordinate-free manner the shapes, right? So it's like completely TDA topological properties. And this is another very important thing, that it studies properties of shape that are invariant or robust to minor perturbation. So this is very important thing in applied science, right? So if you have some minor perturbation, it will not change much. The result or output will not change much. And this is another important thing, that it deals with compressed representation of shape. So it has an application like, suppose I have 2 data sets from 2 different sources. So I can study these 2 data sets combinedly with this TDA technique. So ultimate goal here is we are bringing tools from algebraic topology for studying complex data sets. And yeah, so I always tell that people say that this is a baby topology.
So you said that you can work with 2 data sets. Could they be data sets of 2 different kinds?
Not different kind. So, yes, kind of. Suppose I have 2 variables. Then I can study combined how they do.
Right.
Yes. So, yeah, so that's something people say, it's like a very applied or baby topology. But still, it has a huge application to study different complex system, complex data set. So and it's emerging, different techniques and tools are developing every day. So this is the pipeline. So like briefly, suppose I have a data set like in a matrix space. So from this data set, I actually apply what is called nested simplicial complex. I will talk in a minute. And then from this, I actually extract different topological feature. Okay, so or topological summaries. Then we can apply different learning methods, statistical methods, or machine learning methods on these extracted topological summaries. So this is the brief idea. Okay, so suppose I have a point cloud X in the matrix space. Okay, so and then we need what is called abstract simplicial complex. So an abstract simplicial complex is a collection C of this point cloud such that if sigma belongs to C, a subset of sigma also belongs to C. It's like a very I say higher level definition. It's not like critical. And if the order is p plus 1, I could say sigma is called a p simplex. Okay. If number of elements is p plus 1, then I would say this is a p simplex. So this is the example here. So you see that is a point here. So I will say this is a 0 simplex. And this is a line. I have 2 points. I would say this is a 1 simplex. And so on. Now, a simplicial complex actually can be formed by gluing all these simplexes together. So it's gluing, like you're adding all these simplexes together. But the properties is that, so intersection of 2 simplexes is also a simplex. So think about these two. The intersection of these two is a simplex. So this is the idea. Very, I don't know. It's not very critical or. So this is the idea actually, and now the question is how can we extract this simplicial complex, or how can we develop this simplicial complex from the matrix space? So there is some methods. So it's called check complex or Vietoris-Rips complex. I'll tell you in a minute. So we are focusing on one. It's called Vietoris-Rips complex. This is a technique. How can you extract topological features?
I have a question.
Yes, sure.
The previous slide. Yeah. So, what do you mean by
intersection?
Like, do we merge them together to get?
Oh, intersection means common things between two.
Can you give me a simple example?
It's like intersection of 2 sets. Think about that. Intersection of 2 sets.
So, like, suppose 1 simplex and 2 simplex system,
So this is. I think this line is common, right? This edge, I would say.
Oh, okay.
Edge is common here, right?
Oh, yeah.
Other is not. Everything other is not. So the intersection of these two, I would say this one, like this edge, and this is also a simplex, right?
Oh, so the common thing between.
Common thing between these two. That's right. Yes. Okay. So this is the definition of Vietoris-Rips complex. So the idea is very simple. Suppose I have a point cloud in the matrix space. So the idea is 2 of these points are connected by an edge if the distance between these 2 points less than some threshold, epsilon. That's it. So this is the idea. Very simple thing. So if the distance between these 2 less than epsilon, I will connect them by an edge. So suppose I have this, so every point are disconnected, then I chose a threshold point 1. Okay, so you see that many of them are connected by an edge. And in the next steps, I increase the threshold, I'll get more dense graph, right? So more of these points are connected, and so on. So this process is called filtration. Okay. Network filtration, we actually say. And the idea here is, and so as you say that I am increasing my threshold. When I am increasing my threshold, I am getting a nested sequence of graph, right? So I am getting this graph, nested sequence. The first one is G1, second one is G2, right? So, and then actually coming, so in each of these steps, I actually extract topological features. Okay, so suppose, let's say how many connected components here. Okay, so I'll just compute how many of them, and how many one-dimensional hole or cycle is there. So I will just count these numbers. Okay, then when I increase the threshold, I will compute how many connected components is here. Here it is 2, and how many one-dimensional hole or two-dimensional hole, because here only one-dimensional hole, and so on. So these actually I am calling topological features. Okay, so yeah, so this is a very simple idea. And now the question is, okay, I actually extracted these topological features. Now, question is, which of them are topological signal, and which of them are noise? Right? So this is the real question here. So the idea is, if one particular feature survive longer in this process, like when you are increasing your threshold, if one is survived in epsilon 1 to epsilon 10, for example, so I would say that this is a topological signal. This has some topological signal. Or if it died quickly, like it actually, I should say did birth at epsilon 1, but it died at epsilon 2, then I would say, okay, this is maybe topological noise. Okay, yes.
So, so you're counting, say, 0 simplexes, 1 simplexes, 2, 3, at every level.
Mm-hmm.
And that's what you're saying, that number is what you're saying is topological
Features.
features.
Yeah, I'm just jumping one thing actually. So I'm saying this is a simplicial complexes, and let me see. I'm saying for each epsilon, this is a simplicial complex.
The whole thing.
The whole thing, right?
Right. Okay.
And then this is also another simplicial complex.
So what do you mean by birth? Like,
Okay, so I'm saying
what do
that.
you mean by
Yes.
persistence?
Yeah. So let me quickly go to the next step. Then it will be more clear. So I'm saying that these two are main topological summaries: Betti numbers and persistent diagrams. So I'll talk in the next slide. So this is the thing mainly, the homology, right? So the homology actually these algebraic features, okay, that actually describe the holes in the space, or in our case, in the simplicial complex. Okay. So and then think about that. I have a topological space X, and I actually focusing on p-dimensional hole. This p-dimensional hole is called p-th homologic group. And the rank of this p homologic group is called Betti numbers. So in other words, I would say how many p-dimensional hole is there. So this number, discrete number is the Betti number. Okay, so yeah, this counts the number of independent p-dimensional hole. Yes. Yes.
Can you please go back to the slide?
Yes.
Yeah.
Mm.
So I'm just trying to see how you construct these simplicial complexes out of the data set that you have to begin.
Mm.
So you say that 2 points are connected if the distance between them is less than a
Epsilon.
certain number, right?
Mm.
So that way you have these one simplices. But how do you construct higher dimensional simplices out of
Oh,
that?
so for this case, I cannot go more than 1. So I cannot go more like 2-dimensional hole. Right? So my data set is like
Yeah, but
for this network.
for getting a sensible, interesting simplicial complex.
Yes.
What is the algorithm to construct?
So it's a ball. So think about such. You are creating ball around the point. So it's creating balls,
Anything
right?
in that is correct.
Right. So think about the higher dimension. Then you are creating higher dimension balls around each point. So if
I think Sarment was, how did you get the one simplices? You are getting the.
Yeah.
so suppose here, right? So
Sorry, how are you getting the two simplices?
Right.
so okay, give me one second. So it should be not simplest, maybe.
We are considering abstract simplicial complexes, right? So if 2 points have distance less than epsilon, then we include that point in sigma. So since sigma is an abstract simplicial complex, then all of the subsets of the
So it's not the geometrical complex, it's an
Yeah.
abstract simplicial
Yeah.
complex.
Right.
so all the subsets of sigma should be in the abstract.
So what's the difference between a geometrical
So, so it's an, for the abstract simplicial complex, it is a set subject to certain properties. and that the intersection will be in this, something like that.
Yes.
carry on.
Yes. Okay. So yeah, it's like for me it's also very complex sometimes. So yeah. So this is the thing. So then I'm counting how many p-dimensional hole in the complex for our case. Like so, for example, here Betti P for our case, for our simplicial complex. Here I am saying that in general. So I have a topological space X. But now I am going to simplicial complex again. Right? So for each epsilon, I have a simplicial complex. I want to count like a rank of the P homology group there. Right? For epsilon equals to 0.1 and for epsilon equals to 0.2 and so on. So this is the Betti numbers. Like then I actually count how many one-dimensional hole in this simplicial complex. Okay. And how many two-dimensional and so on. So this is the informal things here. So Betti 0 is the number of connected components, and Betti sub P is the number of p-dimensional hole.
So the homology groups, are they abelian groups here?
I'm not sure. I'm not sure. I'm not sure that part. Yeah. So yeah. So for example, here this is a very simple example. Here, suppose I have a point which is filled in, right? There is no hole there. So then my Betti 0 is 1, right? Only one connected component. I have Betti 1 is 0. There is no one-dimensional hole, and there is no two-dimensional hole, right? But here I have a cycle here. My Betti 0 is 1, right? Only one connected component, right? And then Betti 1 is 1. I have one-dimensional hole here, right? This is a hole, right? And no two-dimensional hole, obviously. But for donors, for example, I have donors. I have Betti 0 is 1, Betti 1 is 2, right? So you see that I have a hole here and I have also hole inside, right? So Betti 1 is 2 and I have one two-dimensional hole. So this is a like very preliminary example. So yeah, so this is how we I understand this is how for each simplicial complex I want these properties. Okay. And the next step is I'm saying that what is the persistent, right? So here it comes. Suppose I have a like nested sequence of topological space, right? So the idea here is now the question is here. So suppose I have a simplicial complex here for epsilon equals to 0.1, then I actually increase my threshold epsilon equals to 0.2. So I actually check. Suppose here there is a one-dimensional hole, right? Think about something like this. Okay. So I actually track whether this exists here or not. Okay. If this hole exists, still I say survive here or thereafter some like longer time, then I will say this is a signal. And all this information I can summarize with a two-dimensional graph. So here I would say x-axis I would say the birth time. Birth time means at which epsilon they actually occur. And in the y-axis is which epsilon they die. Okay, so I summarize this information, this graph, and this is called persistent diagram. Okay, so I'm showing this like this. Okay, so this is a like multi-set. This is their birth time and their death time in the square. So here their birth time means epsilon, and here their death time. So as you see, these black points here are the number of connected components. Betti 0. And these red triangles for one-dimensional hole. So you see that the points or these features which near this diagonal line is the noise, because they die quickly after their birth. Right? So think about this point, like it born here and die also there, right? But these points, think about which are far away from the diagonal line. They survive longer, right? So I would say these points, these features convey some signals, right? So this is the idea here.
That point cannot be sound. That is outside the line. I mean, sound die immediately, you said. So that cannot be sound. we should done in everything from
Sir, I'm.
biology to
No, it's fine. I'm also from statistics. Right. So signal, yes. So it's like in general idea that okay, if they die quickly, they are not signal. But if they survive longer, they might convey some information in the data set.
So I have one question.
Sure.
So when you say the hole disappears, actually for epsilon equal to 0.2, you will have more edges. So how can the hole disappear?
That's a good point, right? So this is okay. So it's maybe filled in. So think about this. It's like epsilon, like one-dimensional hole, right? Then maybe it's filled in inside when you increase your threshold. This is the idea here. So this is not one-dimensional hole here, right? This is the idea. So you are only focusing on holes, three-dimensional holes. Okay. Okay.
And I guess edges, this is a high-dimensional thing, right? Edges can cross
Right.
each other.
Right. Also cross each other. Yes, like
For it to be able to
like so. Think about this. So maybe like this. Okay. In the next step, it will be like this. Okay. So this is the idea. So it's actually disappear not. It's actually converted to higher dimension. Okay. All right. So yeah, this is the idea here. And then so when we compute this persistent diagram, this is a like figure, like image. It's really tough to work with. So you want to do some statistical analysis or machine learning algorithm you want to apply. It's really tough to use image, right? So that's why here we actually convert it to a persistent image based on some Gaussian kernel. So this is the idea here. So there's two steps. You map your persistent diagram to a persistent surface with Gaussian kernel, and then so you integrate for each point. So it's like you have different pixel here. For each pixel, you integrate everything. Right? So you get some vector. So finally, we actually vectorize this persistent image. So I got from here a vector. Okay. Then we can use different statistical or machine learning method in this persistent image. So this is the idea here.
Sorry, could you define persistence image again?
So these are the steps. So again, I said that suppose I extracted this persistent diagram, right? Birth and death time, this figure. So it's not easy to apply in any modeling, statistical modeling or machine learning modeling because it's image, right? So then the idea is, can we convert to some kind of vector, right? So this is the idea. So it has two steps. So you actually map this persistent diagram to a persistent surface, okay, with this Gaussian kernel.
Well, but our data set is discrete, so how?
That's right. So yeah, that's a good point. So I think we actually ignore one more steps here. There is another steps there. So think about this. You are mapping these things to another persistent surface with this Gaussian kernel. Think about this part first. And this is a weighting functions with this mean, okay, and there's variance. So yeah, it's really a little bit tough. I was also reading like a couple of days ago exactly how this works. There's a very big paper that's coming in last year, maybe in machine learning research. So everything goes step by step. So I don't want to go deep, but this is the steps. So you are trying to convert your persistent diagram to a vector with this Gaussian kernel application. Okay, so and think about this. So suppose I have this persistent diagram, right? So I have here is triangle maybe, right? So here is united components. So I actually so you see that I here. So I is the set of all these points here, the triangle, this. So this is the all set of these points. Okay, so I actually convert all this information to based on this Gaussian kernel to a vector. I don't know if it makes sense or not, but
What's a Gaussian kernel doing? I mean,
so
is it probably distribution or something?
yeah, this slide, yeah, it's like two-dimensional normal distribution, you said. Okay, so yeah.
So there has to be an extra square. X minus.
Yeah, yeah.
Oh, okay. Oh, yes, sorry, yeah. Sorry, yeah. Yeah, this is a typo here.
You said
Yeah.
it's a vector. Where does
Vector representation of this persistent diagram. This is the main idea. So I want a vector representation of this figure.
So where's the vector?
Oh, so, okay. So finally, oh yeah, that's something I actually ignore many steps here. Finally, we vectorize here this persistent image. Then I got the vector. Okay, so yeah.
So, what do we mean by vectorizing this?
Okay, so these steps you will get a matrix. So you are getting a matrix here.
You mean flattening? Are we flattening it to make
Yes, this is the thing. So because again you cannot use this matrix in statistical modeling. So I am just vectorizing. Yeah, vectorizing this.
It's like flattened in mathematical.
So you have a matrix, right? So I am just
Also,
I have a matrix here, right? So I am just using this row here and the second row here and so on.
right.
Yes,
right.
this is the thing. Very simple thing. Yes, yeah. But maybe I am missing some information here. But this is the thing that you have to sacrifice. Okay. Okay. So yeah. So this is the summary of TDA for a network. So what actually we said, I am just summarizing it here. So suppose I have this network. I do some graph embedding algorithm, and I use this metric point cloud, and then I use this filtration. And from this filtration, I extract these two features: persistent diagram and Betti numbers. And from persistent diagram, I compute vectorized persistent image. Yeah. And the graph embedding, so there are multiple algorithms there, but the simplest is so you have the distance matrix between two nodes. You just plot it here.
I have a question. Is it the Euclidean metric?
Yes. Yes, this is the simplest one, but now there are lots of fancy algorithms there, especially for multi-layer network. So suppose you have lots of interaction between two different networks, and there are approach here. So let me see the time. I'm going slow. Oh, let me. Sorry. So yeah, let me go quickly then. So let's briefly talk about the algorithm we propose using these TDA tools. Right. So the objectives here, you see that we can model different types of complex system like transportation system with complex network, temporal complex network. So, but the issue here is these complex systems are vulnerable to different hazard. It could be natural hazard like hurricane or earthquake, or like some intentional attack like terrorism, right? So think about the U.S. airport, yeah, right? So if one JFK stops somehow, then everything will be collapsed, something like that. So here we actually want to identify these anomalies in the temporal network, okay, based on this TDA approach. Okay. So in summary, suppose I have this temporal network, right? So I have G1, G2 up to GT, right? And then the main goal here, I want to identify a network snapshot. That means suppose G2, which significantly deviate from normal situation, right? So which behave behave unexpectedly compared to their normal graph distribution. I would say graph distribution. And so this is the summary you should say. Suppose I have a network GT. I want to check whether this GT, think about that T is 10. Okay. So this G10 is normal or abnormal. So then I am comparing this called G sub n. I am saying this G sub n is a network which is normal. Okay, so this is a normal which shows normal behavior. So I need a function, score function, right, which can gives you this G goes to R. Then you can compare. So I have this, suppose one score, I have this score, then absolute deviation of this score. If this is greater than some threshold, I will say that this GT is an anomaly. This is a very simple idea.
What is the basis of setting the threshold?
Yes, sir. This is a good question. That how can we select the threshold? So yeah, it's like very subjective. So experimentally. Okay. So yeah. So in our example, I will show you that how we compute. So yeah. So but now the question is that okay, this is just another anomaly detection algorithm or not? So why we need another algorithm, right? So I always say that okay, I can see that every week or every month we have a new algorithm right. So but again our main focus is local geometry, I would say. So most of the current method, they are focusing on this global topological properties, okay, or lower order, they are focusing on lower order interactions like edge level information. But what about their like higher order interaction? Think about the motif. Right. So think about, I'm saying that during this Hurricane Harvey, like what about the connection of different places locally, like in a community, like in a maybe 10 miles area. So how they are connecting. But if you use this existing algorithm, they are mainly focusing on global things. Okay, so like what is the diameter, how the diameter affected by this hurricane. But now I am focusing mainly on how they locally affected. Okay.
To capture more information.
Right. So this is our main goal here. That what about? Let's see how we can quantify. The question comes, right. So yeah. So we can use this TDA techniques. So remember the issue. So the advantages is, so you are starting the system with different threshold, right. So epsilon equals to 0.1, 2, and 3. Then you try to combine all this information. So you are starting the data set in a multi-lens, right? You are seeing you are starting this and this and this. So you are checking how they behave under multi-lens, right? So this is the like advantages of TDA. Okay, so yeah, so here we.
So I have a question. Sorry, you may have answered this already, as I went to the bathroom. What do you mean by an anomaly?
Okay, so yeah, so I said here actually, this is very subject. So I'm saying that, okay, so this is my network. So I want to see this is abnormal or not compared to their normal graph distribution. Yes. So sir actually asked me how you select this threshold. So I'm saying it's very experimental things. So for our example, I'll show you so how we select this threshold. Okay, so yeah, here we actually use this TDA technique, and mainly we want to focus on local interaction. We are saying local geometry of the network. Okay, so, and this is the steps. So very simple steps, what actually we applied. So suppose this is our temporal transportation network, right? And for each snapshot, right, think about t equals to 1. What actually we do, we compute number of 4 node connected motifs. Remember we have these motifs, right? So for example, for the first network, I compute how many different types of 4 node connected motifs. And then I apply these TDR techniques in this snapshot, in this network, and we extract this sequence of Betti numbers and vectorized persistent image. Okay. And then I actually evaluate these informations. And from there, I actually conclude, okay, this snapshot is normal or abnormal, right? So in other words, it is an anomaly or not. Okay. Then I move to the next one and next one. Yes.
So what is 4 node connected network?
So it's, remember I said initially that, so this is a subgraph, right? So first one is this, I said M1, and maybe this is M2. This is subgraph in the network. Okay. So I say multi-occurrence subgraph in the network. So suppose these types of subgraph, not only one, maybe multiple, maybe 100 in the network, right? So it's like you're just counting. This is algebra things. You're just counting everything. Okay, so yeah, so and then I'm going to the next graph and so on. So now I have this information. For each snapshot, I have number of motifs, I have sequence of Betti numbers, I have vectorized persistent image, right? So now, for suppose think about I have sequence of Betti numbers. So I want to compare this sequence of Betti numbers for different t, and from this information I will say that okay, this is anomaly or not. So for this purpose, I actually use what is called non-parametric data depth. It's a non-parametric approach, kind of robust. So let's briefly talk about that. So yes, sure.
How do you get a sample for G sub n? It's normal.
It's not a sample. Now I'm not saying about sample. So I have a network. Think about US airline network. So you study in January 1st, right? You have this network, right? Number of nodes and number of edges. Then again you collect the data for January 15. You will get a different network, not exactly for January 1st, right? Similarly, maybe February 1st, right? So these are my G1, G2, G3.
Where are you getting the reference normal network? Like you are telling
Yes, okay. Yeah, so that is the question, right? So how I define, okay. The question was, so I'm saying that this is minus f of g, and if is greater than some threshold, right? Some threshold, then I'm saying that this is an anomaly. So this question is how I define this. Right? So we'll talk. Okay, we'll talk in a minute. Okay. Yeah, this is a good question. Okay, so data depth is a like non-parametric technique which actually measure how deep or how centered a particular observation in the data set compared to the whole data set. Like suppose you have a multivariate data. Okay, so it actually gives you a score to each observation, 0 to 1, like 0 to 1. Okay, so an observation with score 0 is most deepest. Okay, let me quickly show you here. A very simple example maybe. Suppose I have a bivariate data set, okay? Bivariate normally, like this. So this depth function actually gives you score to each observation. Like maybe this is the depth 1 and this is the depth 0. 0 means most centered and 1 means most outlying observation. This is so simple actually. Okay, and the outlyingness is the inverse of that. You see that from the name. So it's the inverse of the depth. And now we have an example here. So there are a number of techniques of depth function. One is called Mohalnovich depth. So this is the definition. So it's 1 over 1 plus, this is called Mohalnovich distance. You see, it's a very simple thing, right? X minus mu prime, this is covariance matrix inverse and X minus mu. Right? So this actually give you this score of each observation. Okay. And this is an like 100 observation from bivariate normal. So it give you this like inner outward ordering of the observation. Okay, so this contours gives you this. It's like multivariate quantiles. Think about that. Univariate quantiles is like a multivariate quantiles. Okay. And we use this technique. Think about that. So if I can say this kind of very like deviate from all other observation. So we are using this technique to our problem. Okay, so but the issue here is, remember, so in each steps of each snapshot, right? So each GT, think about this. This is G1, this is G2, and so on. So for each snapshot, I have a sequence of Betti numbers, not one. So I apply this filtration, different threshold. For each threshold, I have one number. So since I have like 50 thresholds, for example, like 0.001, 0.002, and so on. So I have a sequence of Betti numbers, right? So this is not one point. So I have a function. For G1, think about, I am considering Betti numbers, okay? So for G1, I have a function. Okay, so think about this is for G1. For G2, I have another function, right? And so on. So, and similarly for persistent image. I have a vector, right? So it's like a function. So now, that's why I need what is called functional data type. So I want to evaluate these functions, and I want to see which of these functions behave abnormally compared to the others. And then the corresponding network is an anomaly. This is the idea. Okay, so this is the technique actually. They combine all information. Initially, they do point-wise, that is point-wise, and then they combine. So they say, okay, this is anomaly or not, this point. Okay, this point is anomaly or not. Then they combine here. Okay, finally you got a score. So finally I got a score for this curve. Like this is a point, I don't know, 0.2, this may be 0.3, and so on. Remember, that function gives you like between 0 and 1. Right? 0 means most depth curve, 1 means most outlying curve. So this is the idea here, and this is very simple and non-parametric, so you are not doing any assumption here. Okay, so this is the idea. So yeah, so now the question is coming to Sar's questions, that how can you define the threshold, right? So I am saying that, okay, for each curve I have a score. Now how can I define that, okay, if the score, if it is greater than 8.8, it is an outlier, like anomaly. Like how can I define this 0.8 or C, right? So one approach is I am saying that this one. So it's like a functional box plot. So remember univariate box plot? So it's like a functional box plot. So I actually see that 50% central region. Okay, so the band, suppose this is the band of 50% here. Okay, so maybe this one is the band. And if a curve is 1.5 times this 50%, then it is an anomaly. This is one approach. It's not very statistical if there are statistics faculties here. It's like, yeah, very like stochastic, you say. But we can do tests also. So you can do statistical test, develop statistical test, or you can use Monte Carlo simulation. Suppose you do like 1,000 times, then you check the quantiles. Okay, you take like, if it is greater than 95 percentile, then it is an outlier. But here think about that, I have a functional box plot. Okay, I actually select this 50% central region, and if one curve is like higher than this, 1.5 times of this, it is an outlier. Yes?
Could you repeat what do you mean by 50% central region?
Yeah, so remember, so suppose I have like 100 curves. 100 curve means 100 Betti sequence, right? So somehow you select like 50, like, okay, it's like a box plot, box plot type things. So you select the distribution, and then middle 50% middle one. Think about univariate case. Let's say univariate case. Right? Remember, this is the minimum, this is the maximum, right? And this is the Q1 and Q2 and Q3, right? So I am using, think about these two. Okay, so if something is here, maybe 1.5 times of this region, the length, think of the length. Okay, so this length. If it is here and it is 1.5, like greater than 1.5 times, then I say this, if this is the curve, this is the outlier or anomaly. Okay, so yeah, you have to do this box plot first and then compare with the box plot, central region. But this is, this is not very statistical, I would say. But in this project we did that. Now we are working on to develop a test. Yes, sure.
So say I have a 50% central region.
Mm.
So how do I construct 1.5 times the 50% central region?
Okay, so every time you have this score, right? For each function you have a score, depth score. So you are working on now scores, numbers, right? So suppose here, okay, I don't know how to create this band here. So, but I'm saying that suppose I have this 0.9, right? So I am not sure how to say. Okay, let's see. For example, how to define 50% here. I don't know. So maybe and this goes to 0 to 1. Remember, it goes to 0 to 1. Maximum is 1, minimum is 0. So something, and then find the central region. Okay, 50% central region here.
No, I understand the
Right?
central region, but what do you mean one?
Or length. Okay, think about, so suppose here I have, I don't know, 0.4, right? Times 1.5. Okay, and think about it, not 1.5, okay. It will be what? And then if the depth score of this function is greater than this, 0.4 times, like, let's say hypothetically, right? 0.4 times this, if this 0.9 is greater than this number, right? Then I would say that corresponding function is an anomaly.
So 0.4 is like the upper.
Upper, like for this case is the upper one. Yes. Yes.
And also another question.
Yeah, sure.
The functions that you are studying, they come from that Banach space that you mentioned earlier.
So
No, in previous, one of the previous slides.
yeah, so this is the general here, right?
Yeah.
So yeah, so this, suppose think about this in general definition for data depth. So suppose I have a like multivariate data set in a Banach space. Then this is the general definition.
And what does the function, where do the functions lead? In that?
So if you see that function is one example of data depth. Okay, so here these x are multivariate samples, and mu are their mean, multivariate mean, and this is the variance covariance matrix.
But the functions that you are drawing there,
Mhm.
G1, G2,
Mm.
where?
Okay, so this is actually I would say Betti P1, for example, right? Betti P2, the sequence of Betti numbers. Okay, then and so using the depth function, not this one actually, this one, I can get a score for each Betti curves between 0 and 1. Okay, now the question is how can I define that? Okay, I am saying that if, next slide actually, I am saying that if one curve with a certain score is greater than like 1.5 times 50% region, then it will be an anomaly. Yeah. Sorry, I'm taking much time. Let me know when I need to stop.
And another question.
Yeah, sure.
So, how does the number 1.5 is similar?
Yeah, that's a good point. This is experimental also. Yeah, this is also very experimental things.
It's like
Yeah, we're taking this is a standard.
it's like choosing a mean and setting a variance.
Based on kind of it comes from there actually.
Variance.
Yes, but still there is an argument why I am taking this. This is the argument there. So that's why it's better to do a test, a statistical test, like test for change point detection. There are multiple tests, but for our case it's kind of different. We are working on these higher order topological features. Yeah, I am hopefully I am working on one project on that. Okay, so yeah, let me quickly go to the case study. So yeah, I am taking much time. So this is the data set. Actually, I am saying that this is from the Harris County, USA, Texas, and this is like human mobility network. So I have 500 nodes, okay, and I have 92 graphs. Okay, so from August 1st to October 31st. And this is the when it is Hurricane Harvey landed and when government announcement disaster and so on. Okay, so yeah. So I'm saying these are the nodes, 500 nodes, and edges represent number of trips between two nodes, and omega is the movement volume. And data set actually we collected from here. Streetlight is a private company. They actually collect all this information. And people from, I don't know, transportation engineering, they use lots of this website. Okay, and so now let's say we have 92 network. I studied their, for example, here motifs, how their motifs changes. Okay, so you see that this is the most dense motif, and this is the period. This is the gray region here. This is the Hurricane Harvey period. So we see that here is like significantly decrease. Right, so it's like percent change. Okay, and it's 7-day moving average. these black lines. Okay, so you see that there is a significant difference, decrease of this motif occurrences, and same for M2 types, same for M3 types. But think about this, right? So M5, it actually not increased, it's decreased, it increased. Why? Because you see that all this is a line type. You see the motif is line type, it's like a big line. So all these dance motifs are actually decreased or converted to line type. That's why it increased here. So let me tell you other way. The local connections in the network decrease a lot. People are not moving locally. If they need, like in emergency, they need to go like long distance, they travel. But locally they didn't. Okay, so this is the idea here. And for this type, they didn't change much. Yes, any question? Yes.
So you're saying that during the Hurricane Harvey, local networks were disrupted.
Mainly.
And
Also the global. But,
yeah, but
yes.
and the line type is the most global of all of them.
That's right. Think about it. This is like this, right? 1, 2, 3, and 4. It goes this. So that's why it actually increased, like everything converted to these types.
And what about the last one?
Yeah, this is weird. Is that they don't change much. This is we call it star-like. It's like a star. Yeah, this is really interesting feature here. They didn't change much. Yeah. Okay, so this is the for motif, and let's check about their Betti numbers. How their Betti numbers change. So remember, so we actually extracted Betti sequence for all 92 network, right? So these are their Betti sequence, all these, with these gray lines. Okay, and then I applied these derivative techniques to find which one are anomaly. So all these reds, okay, let's say this blue one is the middle one. Okay, median depth, 0 depth. Okay, the blue one.
So,
Yeah.
are we considering the blue one to be the sort of normal one?
Not actually. We are comparing everything together. Okay, it's not like variance, like I'm using the mean, not like that. So I'm using everything together. But this is the depth, like most depth one, like center one. But these reds are the anomalies. And these are actually for related to this COVID, Hurricane Harvey. Okay, so this is the Hurricane Harvey period.
Well, another question.
Yes, sure.
So we define anomaly as the absolute value of FGT minus FGM
It's like
greater
yes,
than
yes,
some
yes.
threshold.
Mm.
So how is this not like normal?
Okay, let me tell you, this is not directly applied here. It's a general definition of a graph anomaly detection, right? So think about this. But here, I am saying that okay.
Here we are considering the 1.5 times 50%.
That's right. This is a normal. Between this is a normal. But yes, it's not directly. I'm comparing absolute value,
Right.
but I'm saying this is a normal. Yes. Okay, so these red curves are for Hurricane Harvey period. And remember, so you can tell me that you may tell me that okay, I can use simple method like average shortest path length. Yes, you might have the similar conclusion. But remember, we are focusing on locally, mainly locally. What about the local interaction change for a like disaster or anything else like abnormal situation? And similarly, the persistent image. So remember, I have defined outliningness opposite of the depth. So you see this area is for Hurricane Harvey. And this is a normalized, that's why it goes down. It should be up, but we normalize. So that's why, so this area are the Hurricane Harvey. Okay, so, yeah, so the idea here is that these techniques actually clearly detect this abnormal behavior in the transportation network. Okay, and this is another interesting result. This is for like every weekday. Okay, so you see the Betti curves, gray curves are the normal curves, the green one is the deepest one, and this is the anomaly. So this technique can be applied to many other fields. Think about Dhaka traffic, right? So you can if you have a standard normal distribution, like this is the normal behavior of traffic, right? If you see something happen here, like it's increasing, it's going above normal, right? Then something happening there. So it is very useful for people from disaster management or different other government institutes, right? So there are lots of research going on in traffic, so normal and abnormal. So, but here again, I am saying that we are focusing on local interactions mainly, based on this TDA technique or motif type techniques.
So I have a
Yes, sure. Sure.
Betti curves. So on the x-axis you are considering xl, right?
That's right. Yes, of course.
So
Yeah.
along the y-axis, what are you considering?
Okay, so think about, okay, let me say this is a number line. This is a number line. So think about for epsilon 1, for example here. For epsilon 1, for graph G, I get Betti 1 is 2. For example, right? For epsilon 2, I have maybe 4.
So
Okay, I am just numbers. Y-axis is a number.
but for one Betti number there is only one curve. I mean,
For one graph. For one graph, I have one curve.
But there only be beta 1.
Yes, yes, I am considering only beta 1 because there is no beta 2, but beta 0 is like,
so
is
these are
not
all
very.
for beta 1.
This is for all, yes, this is for all one-dimensional whole. Yes, yes. But think about this is like all these numbers for different threshold. So this is the important thing, that you are starting the system with multi-lens. Right? Okay, so yeah, so this is the discussion we have applied these TDA techniques to study anomalies in the transportation network. So we found it's very useful. And let me quickly, these are the softwares. Yeah, we are using. The first one is all network summaries. It's called iGraph. There is a Python iGraph also. And for TDA, there are multiple software available for TDA analysis. And for this data depth and functional data analysis, there are some other R packages. So we use these packages and softwares. And this is the future plan. If give me 2 minutes, I'll be done by 2 minutes. So this is the future plan. I am particularly interested on multi-layer network. Remember I told that think about not only transportation system, think about telecommunication system. Right? I have transportation system, in the top I have telecommunication system. They are highly connected, right? So I can model these two complex system with a multi-layer network. Right? So they are connected, right? So think about, I have 3, right? Think about the power grid. I have 3, right? My transportation system, telecommunication system, and power grid network. So and they are connected, somehow they are connected also. Some nodes are connected. Think about the airport, right? In the airport they have line from power grid and also telecommunication system. So we can study this complex system, interdependent complex systems with multi-layer network. Then what about their change point or anomaly? Right? If something happened to power system, it might influence other two. Right? So we can study the dynamics of this multi-layer system, right? So we can use this similar change point detection algorithm can be used there also. Because think about this is the TDA, higher dimensional case. Okay. And I'm also, as a statistician, I am also interested on that, reliability or robustness of multi-layer network. If something happened, how quickly it influenced to other, right? And another thing is diffusion process in network. So think about social network, right? So if some information, how information spread on social network, how we quantify, right? Think about nowadays, people said, okay, now what is called fake news. So how they spread in social networks, Twitter or Facebook, right? So how can we model that? Or think about the COVID case, right? If you think about the network, spreading of COVID through a network, Now question is how they spread. Okay, so this is very interesting topic. I actually started reading on this last 6-7 months. This is very interesting area of research. I'm really interested. I'm working with one of my students in that topic. So another thing is, so we can study multivariate time series. So so for like, suppose time series with 3 dimension or 4 dimension is okay with the existing models. But think about this macro level, macroeconomic variables. Like I have 50 variables, very high dimensional data set. So I can study their dynamics with this TD approach. Okay, so we can do that. And again, so this they call structural breaks or change point detection in this multivariate time series. And this is particularly, I am interested as a statistician, because this is a very new field. So everything is like developing. And the question is, remember I said, okay, if greater than 1.5, it is anomaly, right? So now your question is, okay, how you select 1.5? What is the uncertainty there, right? What is the uncertainty of my conclusion? So that's why I need to do a test, statistical test, which actually capture this uncertainty. Okay, so this is a very good area people are working on now to analyzing all statistical inferences on TDA or in motif type analysis. And another thing, so image processing. There are huge applications in image processing. Think about satellite image. So we have a satellite now, right? So it's a huge application. I don't know. So if we get the data set somehow, or if we can, I don't know, if we can convince or say that, okay, this is how we can analyze the satellite image data and get a conclusion, right? So there is a huge application there also.
You should write a project proposal for this somehow.
Yes, it's a huge application there, right? So yeah. But data sets are not available. And also in neuroscience, a huge application in neuroscience. And also in cosmology. So I know one person from, I think Notre Dame or Vanderbilt. She actually working on TDA techniques on cosmology.
Is it like the filament structure of the universe?
I not know much. So I know that he is working on cosmology. Yeah. Yes. This kind of image, right? They got the image and then analyzes with this TDA. Maybe something like that. Not sure exactly, but people are using image analysis in cosmology. Yeah, thank you so much for your attention. This is the few references. This is for my reference, but if you want like long list, I can provide. So this is my papers, and this is the work is not here, but it's not published yet. So we submitted one time, we got rejected. So now we're working on it. So this is this is very preliminary things.